Alright, you guys ready? Have you been practicing on Verilog? No? Okay. So what we're gonna do today, it's should be quick. We're just gonna write a Verilog file, quick Verilog file. We're gonna go and synthesize it. Then we're gonna obtain the layout of that Verilog file, and finally we're gonna take it into Cadence and get the schematic. Okay? Sounds like a lot of things, but they're pretty straightforward. So first thing, let's just write the Verilog file we want. And this could be like a quick review for Verilog for you guys. So the steps are, as usual, you go to the directory you want and you write cat setup 45, the same thing. Now let us quickly create the Verilog file, okay? Let me make an 8-bit adder, okay? So let's call it adder 8bits.v. I'm just gonna use a command line editor called vi. So we start with module, let's call it adder 8 bits, like this, and it takes A input, B input, C input, and the output, let's call it S. And here we specify our inputs and outputs. So input, so first we need to create a parameter for the width, and let's just start with 8. So here it would be width minus 1 to 0, A, B, and then a single bit input Cin, and an output. The connection's really slow today. And an output, same thing, width minus 1, 0, S. Now there's a really quick way to do the adder, and it's we just assign S equal to A plus B plus Cin. Would this work? Should work, right? The Verilog experts, guys. Okay, I'm gonna assume it works. Oh, what? Yeah, there's an end here. I just wanted to add I want it to be a synchronous design, because when you synthesize something, it usually has a clock and frequency. So I'm gonna make this a synchronous adder. I'm gonna add a clock, okay? So there's gonna be a clock, and always at positive edge of clock, I do okay. Oops. Okay. So I want S to be a register. Register width minus 1 0 S, and then I can't do this anymore. I'll just write S equals to A plus B plus Cn. Okay, this is my adder. I don't know if it works or not, but this is it. Let me just quickly try to compile it. I have a syntax error at line 13. Oh, yeah, that's line 13. Okay, so it's at end module. Okay, here we go. So this is my Verilog file. This is not the best way to design an adder, by the way. Adders are not synchronous like this. Don't take this as a good example. We don't have a clock in an adder. I just made this, I forced it to be synchronous because usually when you synthesize something, it needs to have a clock. Okay? Now, we go into our synthesis stage. Now, for synthesizing, we have a software that has a nice graphical interface, but you need to go into menus and specify parameters and all that. But we also have a script, quick script, that you can just with one command it will synthesize your whole design and give you the results. So you don't need to open any software, you just run that script, and which is much easier than going into that graphical interface. But there's only one thing you need to do, which is go into that script and modify it. So that script is called compile DC, and you will find it in your directory once you start working. You'll find it there. And all you need to do here is, you can see there are two sections. There's this section and then there's this section. Now here it says no modifications needed, so all the modifications you do are on top of this section here. The first thing you do is you specify your Verilog files, all your Verilog files. In my case, I only have one, but it's always a good practice to divide your project into multiple Verilog files. Like if you're doing an FFT, you probably have 6 or 7 different modules. Each one is in a file. Okay. So the first thing is specify my files. What was my file called? ls it was adder 8bits.v. Okay. So adder 8 bits.v. The second thing is we specify our top level module. The top level module is the module in which all the other modules are included. Now, that's how conventionally you design Verilog. You have a module on the top in which you put all the rest of the modules. It's like a hierarchy. So here you specify the top module. In this case, I only have one module because my design is really small. I think I called it adder 8 bits like that. Sorry. Without any slashes. Okay. Now here I specify my clock pin minus capital letters. This is just the name of your clock in the design. And here the clock frequency. Now when you first doing your design, you probably don't know what frequency it runs in, so it's better to start with a low frequency and then see if you can increase it. So let's just leave it at 100 megahertz for now. Okay, just 100 megahertz is really slow for 45 nanometer. And by the way, you see in the Verilog I wrote A plus B. But which kind of adder is it going to be? Is it going to synthesize it into a carry look ahead adder, into a ripple carry adder? What's it going to be? The synthesizer will actually automatically choose which one you want for you, according to the frequency and the area constraints that you put, and there's a bunch of parameters. But it will find the best design that it can. And here the input delay in nanosecond and the output delay. This is how long it takes for the input before they're ready for your module. You can leave it at 0.1 nanosecond. For here you have to know how your design will interact with the rest of the environment around it. But you can just leave it at 0.1. So you can see not much things to modify here. It's pretty straightforward. Okay, and you can open this file in gedit, by the way, like this. Gedit compile. It's the same thing. Now we go into compilation, and here we have to start the synthesizer software, which is called it's called, just a second, DC, I think it's DC shell. Yeah, it's DC shell. Okay. The graphical interface is called Design Vision, a different command, but unless you need something from there, you don't need to start it. So we start DC shell. So this is a famous software by Synopsys. Here you'll see a bunch of errors, but they don't really matter. Okay? And you will be left with a command line like this. Now here, what you want to give it is just that script that we edited, right? The compile DC script we just edited. That's the only file that this software needs. You just give it that file, and that's all you need to do. So here there's a command, let me remember it. I think it's forgot about that command. Nope. Does anybody remember what command it is? Okay. Script, compile. Could be exec, not sure. So let's just try exec, compile. It's not exec. Oh, here we go. The command was right here all the time. So that's just the command that you do. Okay. So you don't need to even enter the software. You just do the command like this, and you give it the script that we edited earlier, which is compile DC. Okay. And here it will take a while. This is a small design, so it will finish early, but if it's a big design, sometimes it will take up to 2 or 3 hours to finish compilation. Okay? And here we'll give you a bunch of warnings you should probably pay attention to. Here it told me that I have a register which has 8 flip-flops. It's still working now, just need to wait for it to finish. So, do you guys know what the objective of synthesizing is? Can somebody tell me? Why do we synthesize? So, netlist of what? Of transistors? No. Well, when we write a Verilog file, we write the behavior of the circuit, right? We go, okay. When you write the Verilog file, you just write how the circuit works, right? Like programming. When you synthesize it, Synthesizer will just give you another Verilog file, but it's on the gate level. So it will give you the circuit on the gate level. That's the whole point of the synthesizer. Okay? So you give it a Verilog file, the synthesizer will give you another Verilog file, which has the gates, how the circuit is made up from the gates. Okay?
So we don't have to create another Verilog file.
Exactly. Yeah. Yeah.
It will create itself,
Hmm?
right? It will create itself.
Yeah, it will create the circuit itself. You have to write the first Verilog file, of course. You give it the Verilog file, it will give you another Verilog file which has the gate level circuit. Yeah, exactly. Alright, so here it finished. There was an error here. I'm not sure what this is, but it looks like it's done. And when it finishes, it gives you a bunch of other files other than the Verilog file, like reports, as in timing reports, power report, area report, all that stuff, and which is very useful for you to put in the project report at the when you turn in your project later. You put the power report, the timing reports, all that information. So let's look at these reports. You will find them under timing, cell, and power. These are the three files that it generated. So the first one is called timing.report. This is just the timing report, meaning did the clock violate the frequency, the maximum frequency supported by the circuit? Is the frequency too fast, too slow? This will give you the timing. And here, and by the way, it's all given in nanoseconds. So, do you guys know what slack is? This is a very important concept in architecture. Slack, clock slack. Clock slack is, if the clock slack is positive, it's a good thing, very good thing. So clock slack is negative, meaning your circuit is not fast enough for the frequency. Meaning the frequency is too fast for the circuit to keep up. So here I have slack of 9.12 nanosecond. This means that my inputs arrive early and they still have 9 nanoseconds before the next clock edge. So I have 9 nanoseconds to spare in my circuit. So I can increase the frequency by let's say, how much is my period now if my frequency is 100 megahertz? If it's 100 megahertz, then how much? It's 10 nanoseconds, so I can increase it by another 10 nanoseconds. Oh, let's say, just to be safe, because you need to leave some slack, if I'm gonna increase it by 8 nanoseconds, so I'll make my period 18 nanoseconds. Oh, right, yes, exactly. So make it 2 nanoseconds. So how much would my frequency be? 500? Yeah. I can probably increase it further, but let's do it anyway. Foreground. Exit. Okay, I'm gonna try 2 nanosecond frequency just to try, okay? I mean 500. So I modify the compile DC file and I execute the synthesizer again. I have to wait for it to finish one more time. Oh, it finished very early this time. let's just check the timing report, see how much slack we have, and there you go. The slack is just 1 nanosecond. So if you get a negative slack, you have to redo your design or decrease the frequency. You cannot have a negative slack, your circuit won't work. Okay? So the slack needs to be positive. And here it will give you the critical path of the circuit. You can see it used the ripple carry adder for this circuit, because the critical path includes all the adder cells. It used 8 full adder cells to create the 8-bit adder, which is really bad design. Anyway, so this is the critical path. So it will tell you what's the worst case delay, and based on that it will tell you the slack. So this is the timing report, which is the first thing you should check. The next report to check is a cell report. The cell report is just how much cells you have and the area used by the circuit. So here I have a total of 16 cells. I have 8 full adder cells and 8 registers. That's all I have in the circuit. And the area is 135 micrometer square. This is given in micrometer square here. That's the default unit for that. Alright, these are the 2 reports we saw. The final report is a power report. And the power report is exactly what it says it is. It's just how much power consumption there is. And you will see that the dynamic power will always be orders of magnitude higher than the leakage power, which is the static power. So here my dynamic power, my total is 155 microwatts. This is 753 nanowatt, the static. By the way, this is just a very rough estimation of the power consumption, because you don't specify any inputs, how the inputs are changing. So this is a very, very rough, often very wrong estimation, but it's worth mentioning. And that's it. That's how we synthesize a circuit. You want to see the Verilog file that we obtained from the synthesis. The Verilog file that we obtain is called, here it will tell you, it's called your top level name .vh. It's always called like that. So this is the Verilog file it generates. So it's .vh. Let's just take a quick look at it. .vh. And you can see it's just it's basically a gate arrangement. It's just a structural level Verilog file. So this is a gate netlist. FAX1 is a full adder cell, full adder. This is a D flip-flop, and wires and outputs and all that. Okay? So this is the Verilog file I obtained. Now let's obtain the layout of this Verilog file. For this, we need to use a software called Encounter. It's the same concept as a synthesizer. I go and edit a script. I edit the script, and then I just perform that script. I don't do anything else. I just perform that script, and I'll get the layout. It's pretty easy. So the process of going from a gate netlist to a layout, what's it called? Do you remember? Yeah, that's the name of the software, Encounter. But what's the process called? The whole process of going from a netlist, gate netlist, to a layout. It's a very famous process in VLSI. No. No. Yes, it's place and route. It's not straightforward to go from gate netlist to layout. There's a lot of algorithms that needs to be run. how should the cells be placed? How should they be routed together? There's a very complex algorithm called place and route. So first the cells need to be placed and then routed. It's all done automatically for you, but it's a complex process. So let's edit the script files for Encounter. The script file that you need to edit is called encounter dot. So there are two Encounter files. You do not touch the TCL file. You touch the .conf, which is the configuration file. Okay? It's important to remember. So this is the file that we edit. Here you edit the top level. What was my top level? You remember? Yeah. Adder 8 bits. So this is not the name of the Verilog file. Remember that this is the name of the module, the top module inside the Verilog code. Okay? So you modify this. Usually you don't have to modify anything here because it's all already named for you. And yeah, this is all. Sometimes if you rename your files, you need to modify the input netlist, the Verilog netlist. But if you don't modify any of the outputs from Design Vision, from the synthesizer, you only need to modify this line here. Okay? That's it. That's all you need to do for Encounter. Now to run Encounter. Now Encounter is the same thing. I can open the graphical interface and do all the work from there, or I can execute the script, and it's easier to execute the script. So I say Encounter. I need to remember that command also. When you don't use these for a while, you kind of forget the name of the command. Whoops. So this is not how you're supposed to do it. Don't do that again. Okay. Never mind. So I'm just searching for the option that I need. Okay. Found it. So this is what you need to do. Encounter config/config, and here the file that we edited earlier, which is .conf, not the TCL file, the .conf file. Okay, this is the command, and now you wait for the software to launch. This is also part of Cadence, by the way, Encounter. Place and route takes a long time to finish when you have a big circuit. In this case, it won't take much to finish. It's a pretty small circuit. But say you're doing an FFT or something, it will take an hour or something. So it's better if you run it on the newer computers, not the old ones. The newer ones are Swamp 36 to 42, 43. If you do it on the 46 and up, they're really slow. And if you have access to the new VLSI PCs, because only I think Dr. Bayoumi group members have access to that, they're also fast. So if you can SSH to these machines and do the synthesis and place and route there, it's pretty fast. So I got an error here, apparently. Okay, this is not good. Let me try to run it on a different PC. The what? I/O buffer? No, you don't. I think Encounter has an option to add it for you automatically if you want. Oh, okay. So I'm not sure why it isn't running, but when you finish this command, Encounter is supposed to open. It's supposed to open and it will show you the layout, including all the metal layers and the poly and everything. It's a really nice figure that it shows you. I want to see if I can open an old layout and show you. Yeah.
If a different color try to compile or synthesize the same fragment of code,
Yeah.
will the code be interpreted in different way or the same? If I use lines or I use Cadence?
You'll have the same you'll probably get different netlists, different circuits, but they'll do the same function as your Verilog code.
And it's quite possible I will get different performance.
Yeah, of course. Because they use different optimization techniques, different algorithms to synthesize. Yeah. So normally you would get all the layout here after you finish. But I want to see if I can open an old layout and show you. I think I have an old layout over here. It's from last semester, spring 2012. So I'm gonna try to open this one and show you how it looks like. Oops. Okay, just forget about this. I don't think I'll be able to do it. Just one last try. Yeah, it's not gonna work. I just wanted to show you the layout and how you can get the area, because from the layout you get an exact area of your circuit. So that's the whole point. Also, you can take that layout and put it into Cadence and simulate it in Spice using all the parasitics that you get from the layout, but we're not going to go over that because it's complicated. So the last thing I wanted to show you is how I can get I can take the Verilog output from the synthesizer, the gate netlist, and get it to work in Cadence. Now when you start Cadence next time, because I will work on fixing this, you will have a new library here called symbols. But because we don't have it here, I'm gonna add it manually. You don't have to add it manually. It should already be here. But I'm gonna try to add it. Okay, so next time you start Cadence, you should already have this by default. This is the same thing as this, except the cells have symbols, and they're connected to VDD and ground. So what I'm gonna do now is I'm gonna create a new library. I'm gonna call it adder 8, and let's attach it. And now that we have that new library, let's import the Verilog file, and we go to File, Import, Verilog. By the way, if we had completed the layout, we could get the layout from here, import DEF, but we're not going to do that. So just import Verilog. Here, which Verilog file do we select? We select the .vh file, the one that we got from the synthesizer. The target library is the library you want to put the cell in, which is adder 8. Close. The reference libraries, this is very important. You have to add the symbols library. symbols, 45 nanometer cells. This should be enough. And we need to add this. It's not enough to select it, you need to add it. And I think that's it. That's all we need to do. Let me see if there are other options. Pre-compiled Verilog. More module. Yeah, I think this is it. Okay, let's see. Okay, it says it's completed. I have a bad feeling about this. I'm sure there's some error. Let's see. Well, there we go. So it's all here. So we have full adder cells like this, and the inputs, outputs. And what are these? Does anybody know? What are these cells?
Registers.
Yeah, they're registers. Okay, we can simulate that if we want to, but I won't do that. I'll just show you how you can go into the individual cells like this. You can do descend, edit, descend, read. Let's do descend, read. New window. So this is the full adder cell that's already in the library. Pretty easy, right? There's nothing hard in what we just talked about today. It's all editing scripts, editing a few lines, and executing commands. That's just it. Okay. Okay, I think we're done. The only thing we missed is the layout, which is fine. If you need that, I can I'll probably make another video by myself, upload it to YouTube. You can watch it. It's pretty easy anyway. That's it. This is our last lab session for this semester. Good luck with the project. And there's a class on Monday, and Wednesday Sean is presenting. That's it.
Monday is lecture.
Yeah,
So you will upload this video to YouTube.
right, yeah.